Greetings again. This is lesson 7. As we continue with where we left off from lesson 6b, and had ended up on the note of the importance of knowing heritability. And we saw that when we know the heritability, it allows us to predict parental traits response in the expected offspring to selection. That's why it's important, because it allows us to predict. It allows us to predict. So this knowledge will let us go on to understanding the concept of the breeder's favorite equation. And I would like us to recognize three important letters. Three important letters. The S, the H, and the R. Very important. As we shall shortly see, that R is the one which associates the multiplication of narrow sense heritability and the selection. That's what's called the breeder's equation. As we progress, we may begin to walk into a little bit of the quantitative genetics, but I've tried to simplify this as much as possible. And that's why I was saying that please ensure that we are walking from somewhere where we were the other time in lesson 6a and 6b to lesson 7. If we jump into lesson 7 without some understanding of the lesson 6a and the 6b, we may get lost. And that's not what we should do, because this is not face-to-face interaction for me to stop and explain something that you may have missed in the previous lessons. So what we want to do is, now that we've talked in very basic format the aspect of heritability, we want to walk from there to predicting a response to selection. And we will use this particular example of a bird. Now, birds become very convenient to study the aspects of heritability and R, the response to selection. Now, as you can see on the left, on the right, you can easily measure, using just a normal ruler, the length of the bird when it's put upside down. Where we can talk about the height of birds, we can talk about the length, horizontal length, when they are put horizontally as seen. We can also even talk about measuring the wings, as you can see below, and also even measuring the rear part of the feathers you can see. You can also use the calipers to measure the length of the feet, so to speak, and the calipers to also measure the beak length. And the beak length, as you can see in the further picture where we have the arrow, is where we will begin to come out and appreciate the aspects of a cross between parents, then get a parent value, then get an offspring value. These data are going to be very important in understanding how we work with heritability to R, response to selection, the S. So here, when we are looking at the example of the birds, we see that quantitative traits in heritability studies, because of the various variation, may not also be that straightforward. They are in fact complicated by the sex differences observed for the trait. But as said before, in studying bird morphologies, one common approach in the previous studies was to compare phenotypic scores of parents and then their offspring. And in that way, we saw, or it was seen, that or can derive the fact that a mid-parent value is often used, and it is defined as the average of the trait value of father and mother. Get to know that. That's where the word mid-parent comes from. It's a value. It's not a parent which is in the middle. It's a value of two parents, an average value. So here, well-known examples in birds include studies of the stature height or length, which can be given by that formula that you can see here, where you can see that it is the average or the summation of the height of the female and the height of the male. And here, the coefficient 108 or 1.08 is a scaling factor. After that scaling, then the mean of the mother's height and the mean of the father's height are sort of leveled. And so here the sex difference can be ignored. So we begin to see here that a mid-parent value can be of use to study and to analyze the data set without hiding the sex effects. Now, in order for the measurements to be useful, they need to be well defined so that measurements taken are consistent and comparable with those taken by others or at other points in time. And we'll see that aspect of the precision when we come to the breeder equation. Now, this comes from the experience that there was a noted sexual difference in the amount of heritable genetic variation in these things, the tarsus length, the wing length, the bill depth, and the body condition index, which these aspects were seen to be actually higher, having higher heritability in females. That's the usefulness of the scaling coefficient. And then the meta-analysis further indicated that heritability in females than in males may be very commonly higher in females. So as a result, in some birds, the evolutionary responses to selection will often be larger in females than in males. Now, let's see how this data were used to estimate heritability derived from the crossing of the female and the male in one cross, then the female 2 and male 2 in the other cross, and the female 3 and male 3 in the other cross. Now, let's note here that F does not stand for F1 or F2 or F3. They stand for female, and M stands for male. These are not filial generations. And so you begin to see that in the calculation between these crosses, we have mid-parent values. And then we have the offsprings that were measured from the crosses. And we see that the offspring values are slightly higher than the parents that were the best parents that were crossed. And we see that the female 2 and male 2 have the 5.31 offspring value. And of course, the higher the offspring value, the better. Because then as you begin to go to heritability, we see a better chance of predicting the success of the response selection. So we can progress from this and look at how we can predict the response to selection. We have the mean peak depth of survivors generally, which was 10.11 millimeters. And then, of course, we have the mean peak depth of the initial or the base population. That was just measured, general initial population, the base, which was 8.82 of the mean base population. So if we take the base population, subtract the mean base population, we would be ending up with S. That's the difference. And let's say that you are given the heritability known to be 0.72. We can actually successfully begin to determine the R, the response to selection. The S is the selection intensity. Distinguish between selection intensity and R, the selection response. So the selection intensity is the differential value which is equal to the survival criterion minus the mean base population. Please try to understand this. Think about it carefully to be able to distinguish what we mean by the survival criterion and the mean base population. The survival criterion is more or less like what we call the life expectancy. All right? Just because in developing world, we may have a life expectancy of 42 years, that really means a lot until we take that and we look at that survival criterion plus some average of a base population. And what we then get is the selection intensity. So let's look at this. We have agreed that in the first instance, we have the top performing individuals from the base population as parents to produce the next generation. That's called a cycle of selection. So we had the 10.11 population mean, and I mean the 10.11 millimeters, and then the population mean of 8.82 millimeters. And if we look at the graph, the bell-shaped curve on the right, we see that we have a parental generation that is bell-shaped curve. And within it, we select parents to cross. The F1 or the female one and male one, the female 2, male 2, the female 3, male 3. And then when we have selected those parents, and then we cross them, then we look at the distribution of the variation among the offspring, the babies. That will be a mini set that is a bell-shaped distribution of what was selected from the parental generation. And so this is how we then progress in looking at the S value, which we now know as 1.29, as I indicated here before. It is just simply a subtraction. And then we have the heritability, which were given here before. And then we have the issue that is the calculation of the response to selection, the R. That R is what is called the breeder's equation. And to improve on it, to qualify it further, it is what is called the breeder's favorite equation. So it takes us to breeder's favorite equation. This breeder's favorite equation integrates 4 essential elements of selection, 4 essential ones. Remember, in it, we've had the crossing of the selected parents. which we selected from the base or the parental generation, and can be represented by this Breeder-Severard equation. We have the genetic gain over time, which is a response to selection. But of course, later on, we'll distinguish the difference between a genetic gain and a response selection a little bit later, because there is a difference of some sort between the two. Then we have that formula, the selection intensity, the selection accuracy, the genetic variance, which is the A, and then over the years per cycle. And a cycle is a complete generation. And we can adjust these things in improving the selection intensity, improving the selection accuracy, improving the genetic variance or diversity, and looking at the years per cycle. So let's look at what selection differential means. The selection differential is the difference between the mean phenotypic value of selected population and the mean phenotypes of the original population. Let's represent it by K. And here we can see that the X sub S is the phenotype value of the selected parents, plants, and the X sub O is the mean of the phenotypic values of the parental population. So the selection intensity, as you can see, is where you can go from 1%, 2%, 5%, 10%. And correspondingly, we now see that the value of K, which is the selection differential, will change. It will become smaller and smaller and smaller. 2.64, 2.42, 2.06, and 1.76. And this is founded in the quantitative genetics, and there are some tables that have been generated to looking at the values of K. We will not go into that now, but for now, we can see that when we are talking about the genetic change in a given time, the R sub T we saw here, it is where you have it as expressed as the intensity, that K, and the R and the A, and that A, as you can see, is really something we'll come to it later, and the genetic variance over the L. So that we have the selection intensity, which is the small I. Then we have this expression here, the A sub AI is the accuracy. And then we have the sigma sub A, which is the genetic standard deviation. And then we have the L, which is the generation interval. So from the foregoing, the message for us to pick is that the breeder equation is represented simply by the R as a product of the narrow sense heritability times the selection differential. That's what it's about. Note again, I want to remind us that the heritability in the narrow sense in the breeder's equation represents the proportion of phenotypic variation due to additive genetic effects. Here, the S is the consequence of the product of selection intensity and selection accuracy, which is multiplied by the narrow sense heritability. So, we want to say here, as we want to conclude this small section, and that's why I'm saying that when we have short timed lessons, I beg you, don't just run through them and say, I finished 10 slides and therefore I'm okay without thinking in between. And even doing a little more internet search to improve your understanding. Don't study the slides, study the message. So it's important here to say that selection response is how much gain you make when mating the selected parents. The R. Remember, the narrow sense heritability is simply a measure of the genetic component that is contributed by the additive genetic response. The response to selection can thus be derived by multiplying the heritability by the selection differential, and the graphs in here, in fact, simply just merely elaborate where we come from. So we're looking at the basis of the breeder's equation to come to the rate of genetic gain. And generally, what breeders are interested in and what they aim for is the the speed, the rate of genetic gain, the rate of the genetic gain, without which progress towards successful selection could be meaningless or simply very slow. Are we together? And they are represented, this genetic gain, the rate of genetic gain is represented by that formula. Please don't leave this section without understanding that formula related to the rate of genetic gain, to the rate of genetic gain, to the rate of genetic gain. All right? So we shall be concluding this session here. Those graphs should become very clear to you as they are represented here, where we have the parental generation, then we have the selected parents within it, who then, when they are crossed, we have a distribution that is offspring generation. And so we can expand the selection response by simply putting those little symbols together and coming to what we have here. And of course, we would get, or we are told that we can determine the selection accuracy by simply taking this aspect of the true value and the estimated breeding value, which we'll see later. So here, let's just go back to an example of this. For example, and we've looked at that of birds already. If you have a population where the mean phenotypic value is 100, and you need a subpopulation with a mean value of 125 to breed the next generation, let's say you need a value to breed the next generation, and the heritability we are given is 0.05, then the response to selection would simply be the product of that times this selection differential, and that would equal to 12.5. In other words, the response to selection in this case, where the differential is 25 units in the parent generation, would be 12.5 units in the offspring with respect to the original population. This is because the narrow sense heritability, the proportion of the phenotypic variation attributable to the variation in the additive effects of genes controls only half of the variation. In other words, they are other components of phenotypic variance, such as environmental variance, as we've seen, which may not be heritable from parent to offspring. And so there is a regression of the population. So there is a regression toward the population mean. And that ends the discussion on this lesson 7A.